Alright, so in order for us to talk about what we're doing in the Gram-Schmidt process, we need to know something about a term known as projections. So let's start off. When we're looking at two vectors u and v with v not equal to the 0 vector, the projection of the vector u onto the vector v is going to be given by the projection of u onto v, so we denote it like this, and it's essentially just going to be the dot product of the two vectors divided by the length of the vector that's being projected onto squared times that vector. So essentially we've got this vector and we've got this vector, and we want to know about the projection. So the projection part is going to be this part here, and essentially it's the part of the vector that we would just kind of, if we had kind of a bit of sun onto here, it'd kind of be the shadow of the vector down here. And so what we do is we take the dot product between those vectors, and then we divide by the length of the vector and then multiply by the vector in that direction. So this gives us this part here. We'd like to be able to generalize this for a subspace and be able to kind of talk about this in general. So suppose we've got a vector in R3 that we'd like to project, and we'd like to project that vector onto some vector here that is a plane. So say there's a vector space, it creates this plane here. We're really trying to look at projecting the line onto that is parallel to this, and so what we're doing is we're trying to apply a transformation from this vector in R3 onto this set L here. So we want to go ahead and find the projection, and how we're going to end up doing that is we're going to actually have to go ahead and project onto all the different vectors that we have in there. And in order for us to find the projection, we're going to end up having the projection of the vector onto that set be the vector that is left over after we subtract all the different orthogonal parts to that set. So definition time. Let V be a non-trivial subspace with an orthogonal basis, then the projection of U onto that subspace V is going to be found by taking the projection for each of U onto every single vector that we have. So essentially we're writing U as a linear combination of the orthogonal basis of V. And so this is going to end up leading to us thinking about the Gram-Schmidt process. So what is the Gram-Schmidt process? Well, this is a process for us finding an orthogonal basis for an arbitrary vector space. So we talked a little bit in the last video about why we want to have an orthogonal basis. And so the Gram-Schmidt process is going to be our process for taking a basis and turning it into an orthogonal basis. So what we'll do is we'll start off with one of our vectors, and we're going to make everything else orthogonal starting with this. So we're going to create it step by step. We have to know this first, so given the basis, we're going to create an orthogonal basis this way. So the first vector that we're going to create in our new basis will be whatever the first vector is of the original basis. From here, what we want to do is we want to go ahead and subtract off the projection of each new vector onto the vectors we already have. So if we want to find V2, we need to take B2 and subtract the projection of B2 onto the first vector V1. From there, we want to go ahead and get our third vector by taking the third vector we were originally given and subtracting off the projection of that vector onto the first vector and subtracting off the projection of that vector onto the second vector we found. And we're going to just keep doing this, subtracting off the projection of each time, so that way we can get something that ends up being orthogonal. So to write this in an alternate way, using the definition 14.9 from the previous page, so that's just on the first page of this set of notes. Essentially, the first vector is going to be whatever the first vector was, and then from there we're going to go ahead and find the projection of each new vector onto the old vectors and subtract it off. So we get formulas that look like this. So let's look at an example of how we would go about doing this. Before we do, I just want to make a little bit of a comment. So Gram-Schmidt process, you notice is going to have a lot of addition and multiplication and dividing. So we got a lot of different things we have to do here. And so what ends up happening is if we end up with a large number of these different dot products we have to do, or if we end up with dot products where we end up with some weird computational flaws, we end up getting things where we end up losing the orthogonality because of round-off errors. There's modified versions of this process that make it a little bit more easy to do with a computer and make it so that it's less susceptible to error. Some of these ways of doing it are outside of the scope of this class, givens, rotations, and householder reflectors. But just so you know, in case you ever decide you wanted to try to program this to try to make your life easier, that programming part might be a little difficult. It might not work out quite the way you want it to, and it's because of some of these round-off errors you can get. So let's say we wanted to go ahead and find an orthogonal basis from this set here. So these are going to be our B1, B2, and B3 using the notation from the previous page. And if we want to go ahead and find a vector V1, well, it's just going to be whatever the first vector is. And so in this case, the first vector is -1, 0, 1. So that'll be the first of the vectors we're going to look at. The second vector that will be in our orthogonal basis will be whatever the second vector is here, but we have to subtract off that vector dotted with the first vector divided by the length of that first vector squared, or v1 dotted with itself, times that vector. So B2 is this 3, 4, 1. And we want to subtract off B2 dotted with V1. Now we've got some of these things here that we've already written for convenience sake, but I do want to make sure that I type them out calculator-wise just so you can kind of get a little more practice in seeing what they look like. So if we want B2 dotted with V1, that will be 3 times -1 plus 4 times 0 plus 1 times 1. When we do that, we get -2. So minus -2 divided by v1 dotted with itself, which I'm saying is 2, but again, just to be sure, we want -1 times -1 plus 0 times 0 plus 1 times 1. And we get 2. So -2 over 2 times the vector v1. So -1, 0, 1. So if we take minus -2 over 2, -2 over 2 is -1, but minus that is 1. So we're really taking 3, 4, 1 plus -1, 0, 1. And so when we do this, we'll end up getting 2, 4, and 2. And so this is going to be our V2. Now it's important to keep notationally track of what's going on here. Whenever we're subtracting off the projection, it's using these new vectors with the vector coming in. So we want to be very careful about that. It's very easy to kind of mistakenly grab one of these when you really need to grab one of these. All right, so let's keep going. If we want to find the last vector it's going to be the last vector here, that's the new one, minus dot product of that vector with the first vector divided by the dot product of that vector with itself times that vector. We also need to subtract off this vector dotted with the second vector divided by that vector dotted with itself times that vector. Again, we've got some of these listed up here, but I want to go ahead and calculate them just to give us a little bit more practice. So B3, we got it up here, is 416. So it'll be 416 minus B3 dotted with B1. So that'll be 4 times negative 1 plus 1 times 0 plus 6 times 1, and we get 2 from that. So we get 2 here. We already know what V1 dotted with V1 is because we did it here. So oftentimes you're going to end up having to calculate things over and over again, which is why sometimes doing this these dot products on the side can be helpful to kind of keep your head straight. So this will be over 2, and then we're multiplying that by negative 1, 0, 1. Then we need to subtract B3 dotted with V2 divided by V2 dotted with itself times V2. So let's first take the dot product of B3 and V2. So these two vectors. When we do that, we should get 2 times 4 plus 4 times 1 plus 2 times 6. We end up getting 24. And then we also need to take the dot product of V2 with itself. We have not found this one yet, so this dotted with itself. So when we're doing that, we'll get 2 times 2 plus 4 times 4 plus 2 times 2. And we should get 24. Well, that's convenient. And then we need to, of course, multiply that by V2. So V2 was the second vector we found, 2, 4, 2. All right, so to continue this, we're essentially saying we have 4, 1, 6. 2 over 2 is 1, and we're subtracting, so minus negative 1, 0, 1. And then minus 24 over 24 is 1, so minus 2, 4, 2. All right, so let's go ahead and do the subtraction. If we want to get the first entry, we should take 4 minus negative 1 minus 2. And when we do that, we get 3. We want the second entry, we'll take 1 minus 0 minus 4, not times, minus. We'll get negative 3. And then last but not least, we'll get 6 minus 1 minus 2, and we'll get 3. You might notice that I'm kind of defaulting to the calculator here and kind of leaning a little heavily on it. The reason for that is that when we have these minus signs between the vectors, and we also have negative signs in here, it can be very easy to make a little small mistake. So that first negative 1 made me go, okay, well, we should make sure we're doing 4 minus negative 1 minus 2. And then the calculator can kind of help us catch things that we might miss or make mistakes on. So this would be the third vector that we're looking at. So now we have it. We have our orthogonal basis. And then orthogonal basis is going to be negative 1, 0, 1. So this was just the V1 we had. 2, 4, 2. So the V2 we found. And then 3, negative 3, 3. And so the question is, if you're doing this on an exam and you wanted to double check that this was indeed orthogonal, how would you do that? So the check here is just to make sure that all the dot products are 0. So we can check by finding v1 dotted with v2, finding v2 dotted with v3, and finding v1 dotted with v3. So v1 dotted with v2 is going to be -1 times 2 plus 0 times 4 plus 1 times 2, or -2 plus 0 plus 2, which is 0, which is what we want. v2 dotted with v3 is 2 times 3 plus 4 times -3 plus 2 times 3, which will give us 6 minus 12 plus 6, which will give us 0. And then last but not least is v1 dotted with v3, so we would have -1 times 3 plus 0 times -3 plus 1 times 3, so that'll be -3 plus 0 plus 3, which is 0. So all three of those were 0, so that would be a way for us to check to make sure we had done it all properly. So keep that in mind. You do have enough time on the exam to not only be able to do this, but you also should be able to double check your work, just to make sure you're not making any mistakes. Alright, so recall that a set of vectors is orthonormal if the set is orthogonal and the length of each of the vectors is going to be 1. So if we have an orthogonal set, we can go ahead and normalize it by dividing each vector by its norm. So oftentimes if you're trying to complete the Gram-Schmidt process by hand, it'll be easier for you to normalize each orthogonal vector as you go. And so the reason for this is that say we were doing this process and we wanted to know what v1 dotted with v1 is. Well, if we had spent the time making it normalized, then this would just be 1 instead. Now, of course, that's going to change what this vector is, and that'll change this dot product as well. But if you were trying to normalize it, it would be easier to go ahead and do the normalization as you go. Now, MATLAB's got a function in it that will go ahead and orthogonalize the columns of a basis. So what you do is you create a matrix of the basis elements, and then you can use QR. You can use this syntax, and Q will give you a matrix with the orthonormal columns. But when you're doing the concepts on the exam, you do need to do the process by hand. So need to do by hand on exam, because I'm evil and I'm a jerk that wants to make sure you actually understand how to do a thing. We can't use technology for everything if the technology is based on our understanding of how to set it up. We only can use it after we know how to do the things. Okay, so say we want to go ahead and normalize this basis. What we'd do is we'd go ahead and find the length of each of these vectors. So we saw that v1 dotted with itself was 2, so that means the square root of 2 will be the length for that. We know that v2, we can find the length of v2 by taking 2 squared plus 4 squared plus 2 squared, which will be 4 plus 16 plus 4. So when we take the square root, we'll end up with 2 times the square root of 6. And then the last will be, this last vector will be the square root of 3 squared plus -3 squared plus 3 squared. And when we go ahead and calculate that, we'll get 9 plus 9 plus 9, which is 27, and the square root of that is 3 square root of 3. So then the orthonormal basis would be found by just going ahead and dividing each of those by their own length. So the first one would be -1 over the square root of 2, 0, 1 over the square root of 2. The next one, if we're taking 2 divided by 2 square root of 6, we'll get 1 over the square root of 6. If we take 4 divided by 2 square root of 6, we'll get 2 over the square root of 6. And if we're taking 2 divided by 2 square root of 6, we'll again get 1 over the square root of 6. In the back of your head, there might be a teacher from grade school yelling at you, well, why are the rationals in the denominator? That's very important. We don't like that. We don't care. The whole point of right now is just making sure we can do the process. And then the last one will be taking each of these and dividing by 3 square root of 3. So the 3 parts are going to cancel. And so we just should end up with the correct sign and 1 over the square root of 3. So 1 over the square root of 3, negative 1 over the square root of 3, and 1 over the square root of 3. So this would be our orthonormal basis. Now, we can call a matrix orthogonal if its basis or if its columns create an orthonormal set. So notice the little bit of the disconnect here. The columns have to create an orthonormal set in order for it to be considered an orthogonal matrix. It's a little bit tedious to think about, but that's the idea. Now, the reason we'd want an orthogonal matrix is that a matrix is, if it's an n by n orthogonal matrix, then its inverse is equal to the transpose. So that's really interesting. That means that we can take the transpose of the matrix and use that as its inverse. So that's kind of really cool. So this is nifty. And so beyond the scope of this class, there are a lot of applications that might be interested in using that. So we could show this on our own by showing that the inverse was equal to the transpose for this matrix. So we just found that this was our orthonormal basis. So by taking it and making it columns of a matrix, that makes an orthogonal matrix. So if you wanted to find the transpose of this matrix, that would end up being the inverse, and you could go ahead and show it was the inverse multiplicatively using the same way that you would normally find an inverse. So if you're looking for more examples of trying to do the Gram-Schmidt process, so this process here, so for more examples, what you should do is start with a basis for Rn. I recommend you let n be 3. 2 is too easy. But 4 takes forever. Try the Gram-Schmidt process. And then check that each of the dot products equals 0 for all the different vectors where they're not equal to. In fact, I'm going to go ahead and recommend posting these on the discussion board. So as you are trying out some different things for Gram-Schmidt, I recommend posting those on the discussion board. You can kind of have a back and forth, make sure you're understanding how the process works, the steps you need to take, and that way you can go from there. Again, some of the common pitfalls I see with this process is kind of getting confused with all this notation. Remember that when you're taking the projections, they're of the new vectors you found, and you're the only thing you're including from the original is whatever the newest vector is. So keep that in mind. That is probably the most common pitfall I see. This is the last mastery concept if your version of this class has mastery exams. So definitely feel as though you can ask me for examples and try different examples, because I know we only kind of had one going through the whole Gram-Schmidt process in the notes.